A very warm welcome to Dr. Udpikar sir. Now I hand over sessions to Dr. Udpikar sir. Thank you. Please sir. Thank you sir.
Okay. Yeah.
Welcome all participants. Thank you.
Yeah. So I'm just writing a message to all. Thanks a lot, and I hope we'll have a good time. Dr. Pise, Dr. Kharvankar, and Dr. Sapkar really appreciate this opportunity to allow me to give a talk here. And I'm also really grateful for a very generous introduction by Dr. Sapkar. So let's hope that today and tomorrow's sessions we can really build some interesting discussion around the technologies of signal processing, image processing, and video processing. So I'm just going to switch to a brief presentation, and I hope you can all see my screen.
Yeah, it's visible, sir.
Yeah, okay. So this is how we'll start. So I think I'd like to start by remembering that it's a very special time in everyone's life now. And we should really start by appreciating all those COVID warriors in our country and several other countries are doing an incredible job in the very difficult situation and still making it possible that we all recover. I think the fighting spirit of humans is extremely well exemplified by these COVID warriors. I'd really like to appreciate them. Now, really happy are those who know what's the best use of isolations. I also tried to learn something. To tell you very frankly, beginning of this isolation period, I could wash table utensils of 5 people in my family in 30 minutes. Now I can do it in 20 minutes. So I think I improved. So there are many advantages of this change situation. One of them is right here, that the College of Engineering in Karad is making the best use of all of us isolated at our homes and still doing a reasonably constructive dialogue on signal processing, image processing, and video processing. I think just a few months ago, this would have been thought as unthinkable that I'm at my home. Most of you are at your homes, and we are doing this conversation. So really, times are changing. We all have to change. And hopefully, I think some of the technologies and some of the interesting applications of these technologies would lead us to a better life through a change. So I'm going to speak about a little bit of our experience in signal processing, image processing, and video processing. Dr. Sapkar was very kind to give me 2 slots. So today it's more about the technology and what is the status of this technology, where it's going in future, and maybe some of the implementation topics, which perhaps only in an industry get amplified. So I'd like to touch upon them today. And tomorrow, when we meet in the morning again, I will show you a lot of case studies of these applications. So I'm really very thankful and grateful that my teachers really gave me very excellent teaching, brought up the background of this technology of signal and image processing so very well. I remember this began in COEP. We had stalwart professors in the area of communication engineering and so on. So they really instilled the interest in signal processing, Fourier transforms, and so on. And with a little bit of mathematical awe, I went to IIT Madras, and even several stalwarts there helped to further this interest. And as Dr. Sapkar told you, I had the opportunity to publish a thesis on image processing topic. So I'm one of those who's really grateful to the core that even today, 30 years after it all happened, I still do pretty much the same things that I used to do in my IIT days. And we have found several applications of this in India and a few outside India. So this goes to show that this technology is extremely relevant. So what I'll do is I'll tell you a little bit about um, uh, the program that we are going to have today. So I think I already summarized this, that we'll talk about the technologies, we'll talk about the key components that go into a signal and image processing technology based application. These are sensors, processors, techniques, and frameworks. I told you about the implementation. So quality attributes in any implementation are very important to an industry. So I'll try to give you our perspective on that. And at the end, we'll look at a couple of future directions in these technologies. So what I was saying is that in the 30 years that have passed since my college days, I could really implement or be a part of the team that implemented a lot of applications in India. And so this is my one slide introduction to what SICOM is. And these are the domains and technologies we work on. Now, before I proceed, I want to ask the organizers, am I audible?
Yes, sir.
Do the organizers hear me clearly?
Yes, sir, you are audible perfectly.
And also the slide is completely seen end to end.
Yeah, entirely.
Because sometimes resolution differences cut the part of the slide. So I just want to make sure before we go further.
No.
So,
Right.
Yeah. So SICOM works in a few domains. And one of the top domains we work in is electro-optics. And we have done applications like laser rangefinders, laser seekers, Q-switch drivers, which are used in very high power laser driving, fiber optic gyros, which are used in precise navigation, and time of flight. TOF stands for time of flight imaging. In fact, this is one topic towards the end. I'll tell you how future directions are really getting decided by these kind of imaging technologies. We also work a lot on digital communications, software-defined radio. So recently, our team has implemented a multi-band, multi-modulation radio concept on a common hardware platform. And we hope that this will be very useful for strategic applications in India. Then we are in SATCOM space. The COSPAS SARSAT receiver is used by ISRO for their search and rescue warning system. And tomorrow I'm going to talk a little bit more detail about this application, and it's useful in saving several lives when there are emergencies like cyclones and landslides and earthquakes and things like that. We've worked in the space of CDMA encoding, UHF transmitter receivers, active noise cancellation. A little bit of this I'm going to tell you today, the technology status. One area in which I think SICOM is really very proud of is the area of radars, and especially wind profiler radars. Now, a wind profiler radar is a device that can give you wind velocity vectors at different altitudes in atmosphere. So it kind of gives you a map of velocity vectors at different heights. And from this, atmospheric scientists can recover very interesting data, which could predict rainfall, precipitation, possibilities of hurricanes and things like that. And practically every major wind profiler that's installed in India uses our signal processing technology. Ionosonde is another such device. Radio altimeters are used in measuring height of an object from ground. These are typically used in aircrafts, as you can guess. And these also are radars. We'll talk a little bit about these things today. Our other two divisions work mainly on industrial automation. In fact, that's our main bedrock of business. And machine vision is a technology we've implemented for the last 25, 30 years in many Indian industries and also a couple of global customers. As the topic of today's discussion is video processing, also some experience in smart security of video analytics could be helpful in understanding the recent status. So what sort of technologies we use? Obviously, we use signals and image and video processing technologies. What that means is that an average or any engineer in our team would know what these algorithms are, what are the best libraries, how to characterize these algorithms, how to test them. And he or she would probably know how to implement this in one of the popular implementation media like C, C++, or Python, or VHDL, and things like that. We also use a lot of modeling and simulation because most of the problems we work on, the pictures you see on the slide and the kind of topics I mentioned, they are very hard to do lab testing because they are really field applications. So we need to do a model of that field and simulate it in the lab and make sure that our system works with the simulated source first and then take it to the field. So this is an extremely important area for us. And as you can guess, many of you are in research and academic field. MATLAB is the medium for doing this modeling and simulation. So we use a lot of MATLAB for doing this. And our technologies are, as I mentioned, hardware, software, system development, verification, and validation. And we use platforms like PLCs, microcontrollers, DSPs, field programmable gate arrays, and very powerful server machines. So here are some examples on this slide. I will not waste time on telling or summarizing them here. You can go straight to the topic, and some of these examples are going to show up in this topic discussion. So let me go to the next slide now. And this I just put together as a kind of a short summary of what are the issues and topics we typically handle when we work on signal, image, and video processing applications. And this also perhaps gives you an idea of what is the present status. So obviously the journey begins at sensors, and the data from sensors goes to the processors, and results from processors go to some kind of actuator. So what kind of sensors? I think sensor is a device that captures any physical entity and converts it into electrical form so that it becomes possible to feed it into a processor and then do whatever you want to do with it. So I think most common sensors most of us carry in our pockets are microphones and cameras and antenna, because our smartphones have all these three sensors embedded inside. Then there can be optical sensors, which convert light intensity into electrical signal. An RFID reader is a fairly good example of a sensor that just senses the presence of a RFID tag. And a lot of practical applications that are based around this. A host of position sensors, which can sense distance, tilt, altitude, attitude, speed, acceleration, rotation, and so on. In fact, a radar in some sense is a distance sensor. And a lot of process sensors, which sense process parameters like temperature, pressure, flow, vibration. This last topic is very close to our automation division's heart. So they use a lot of these sensors and PLCs to implement accurate automatic control in industrial applications. So in each of these sensor types, the state of the art today is fairly well developed as compared to how these technologies started. So from a microphone, you might have seen in old World War II movies, which look like a 1 kilo device. Now you have something that weighs maybe micro or milligrams, and that is sitting inside your cell phone and is probably far more sensitive than that 1 kilo microphone that existed 50 or 60 years ago. I think for this, a lot of credit goes to scientists from other areas, the materials innovations that have happened, technologies that revolve around materials that have happened, which makes us makes it possible to make these sensors small. Camera, I mean, when I was doing my PhD research, we had only one camera in our lab, and that was a Vidicon camera. And I remember it weighed a couple of kilograms. It was very difficult to mount it on a tripod and take a shot of what I wanted to do. And today, again, needless to say, I think most of you carry 40, 50, maybe 100 megapixels in your pocket. So the state of the art really has come a long way and is going further. And one such example I'll be talking about at the end, what's happening in the camera imaging technology. So goes with the actuators, which convert the electrical signal back to some physical entity. So headphones, loudspeakers produce sound, displays produce pictures, antennas produce RF signals that go into the air, light sources produce light, and then there are servo and motors and gimbals that can produce position information. So these are all, again, things that convert your electronic information back to physical information. And then come the area of processors. I think when we say we work in signal processing, mostly we mean that we work on processors doing signal processing. So this middle topic is probably the most important, with which we spend most of our time. And today, microcontrollers, DSPs, FPGAs, system-on-chip devices, they are all architected for fast, precise, and large-size data processing. And the other interesting feature they have to provide is to be able to communicate with the rest of the world. So your smartphone sounds so interesting because it's got Wi-Fi, it's got Bluetooth, it's got USB and near field communication and whatnot. So I think these interfaces really make the device very useful. And architectures of these processors, their unique capabilities have come extremely long way. I think go back to my college days. We had an 8-bit microprocessor kit in our college. And I remember the assignment given was to build a Viterbi encoder on this board. How challenging it was, because everything was coded in assembly language and so on. Today, I think the techniques have become so matured and frameworks have become so matured, which are the next two topics, that you can almost pick up something that you want off the shelf and integrate it with your scheme of things and build your application. So this is an area which is, I think, we can spend a lot of time talking about. Hopefully, I think a couple of examples I'll give you in subsequent slides. I'll have an opportunity to enlarge this a bit. Then come the techniques. These are like typically our interview questions. When somebody is wanting to join our company, we would ask him, do you know what are digital filters and the FIR filters and the IIR filters and the difference equations and how coefficients decide the filter response and so on. It's a very important topic. I think almost everything we have done probably has one or the other digital filter inside. All kinds of transforms, the Fourier transforms, wavelet transforms. I think these help you to interpret whatever data you have from the sensor in a completely different perspective, that is in the frequency domain. You get to know its dynamic behavior rather than just the static behavior. And then there are techniques like covariances, least square fitting, iterative procedures, simulation tools. I missed a few there. Digital down conversion. This is an extremely important topic whenever we are working in any communication project, that the high frequency signal is to be brought down to a manageable intermediate frequency by some kind of down conversion. This is an important technique too. And finally, there are frameworks. So these are ready to use optimized libraries. I think today a youngster can do a far better and far faster job because he or she is so adept to searching what is available off the shelf. And this sometimes I'm very unhappy about myself that we seniors tend to think that everything has to come ground up, but that's not really necessary. Many things are really done so well in these optimized libraries, which are fairly ready to use. And in a sense, I think in the last 5 to 10 years, younger engineers have opened our eyes and told us how things can be done much better and faster. So there are schematic tools like GNU radio, for example, is a very interesting schematic tool where a software-defined radio can be configured at the schematic level. Its performance can be analyzed and then it can be converted into a real hardware-based implementation. There are a bunch of ARM-based libraries, ARM being a very popular processor architecture. And these libraries do signal processing, again, very effective. So I can quote here one thing. About 10 years ago, to do an 1K FFT under, let's say, a millisecond, we relied on a powerful, expensive DSP. Today, it probably can be done on a few dollar microcontroller. And that's, I think, all thanks to, again, these kind of optimized libraries that come with the microcontroller. And last but not the least, I think the way the world is changing, sometimes it gives me a very sad feeling that getting completely outdated by this machine learning, deep learning, these technologies, where it's not even any more necessary to keep making your own algorithmic scheme. The scheme itself can be figured out by deep learning. And then there are frameworks like Caffe CNN, YOLO, TensorFlow, and so on. And again, some of our younger engineers have really brought up astonishing results by using these frameworks in some of our projects. So this, I thought this one slide captures, I think, all the interesting topics about signal, image, and video processing. And when we go into the next 5-6 slides where I talk about individual application domains and the status, probably you will get more meaning out of this. So let me do that. Let me move to the first such example. This is a signal processing application. So how do I distinguish signal processing, image processing, and video processing? So signal processing, by and large, we understand, is a one-dimensional task. There is something that's a function of time. It could be audio, it could be vibration, it could simply be a process parameter. And I'm doing something to that to get a desired result. So in this particular domain of audio signal processing, we have built a device called Mobidio, and you see it here on the slide. As compared to a 2 rupee coin, it's a pretty small, lightweight device, and it uses, as the slide says, a very low power ARM microcontroller. On the top of this board, you see a USB connector. It's supposed to plug directly into a cell phone. So it's supposed to work with the cell phone's power source. So hence, it's a very low power microcontroller. It uses onboard sensors, which are MEMS microphones, and they are beamforming microphones. So they can be used to control the sensitive direction from which the source sound is coming. And the actuators are headphones and speakers. And we use techniques like digital filters, fast Fourier transforms, autocorrelation function, coherence function, and beamforming. All these run on that tiny low power microcontroller, by the way, using a framework of highly optimized ARM libraries. Now, what are we getting out of this? We are getting active noise cancellation. So in a situation where there is a very strong background noise, the called party does not hear your voice very clearly. And this happens in many situations, at railway stations, at bus stands, in a meeting room, or in your own drawing room when your family is watching a television program and you are getting a call. So our objective is to, in these kind of situations, by simply click of a button on the screen, it's possible to bring in this additional cancellation and make the communication more intelligible. The other application of this is, of course, hearing enhancement. We are presently working with an expert team to see how this could be used for hearing impaired persons so that they hear better with this kind of technology added to a cell phone. So the state of the art here is the MEMS microphones. We are using from a company that is probably supplying these microphones for 30 to 40% of cell phones worldwide. And they are very tiny. I think they weigh just a few milligrams, and they directly solder on the PCB. In fact, on this board, they are probably on the back side, so you don't see here. And they give very accurate and good SNR conversion, direct digital output from the microphone. These are interfaced to the microcontroller on a bus like an SPI bus. Some of you might be familiar. It's a synchronous serial bus which has a clock and data pins. And sometimes even at clock frequencies as high as 10 megahertz, you can clock this data into a processor. And then the processor does all its processing that I have written under techniques, and then sends the output to the speakers or back to the cell phone so that it can be heard on the cell phone speakers. So this makes a very typical audio signal processing application. And we are hoping that a lot more things like speech recognition and things like that could eventually be ported on this board, and our teams are working on this. So this was one example. Let's go to the next example. As I said, we are fairly proud about our radar line. Or practically every wind profiler in this country uses our processor. So the box you see below has a bunch of processors inside. It's Xilinx Vertex 5 FPGA, although today this FPGA is almost out of business and they have replaced it with better versions. But when we built this box about 7-8 years ago, This was one of the top of the line FPGA devices. It uses analog devices, Tiger Shark DSPs. These are 32-bit number crunching chips. There's a Power PC and there is Gigabit Ethernet hardware inside. And our team has put together all this hardware on our own PCBs. So it's kind of a customized piece of hardware. And what does it do? What you see on the right side above the box is what is called a Doppler spectrum. The x-axis of that is frequency and the y-axis is height. And the height is in kilometers from surface of Earth. And the x-axis, which is Doppler frequency, in a way tells you what is the wind velocity. Well, most of us know the Doppler effect, that when you send a periodic signal on a moving platform, then the moving platform's speed in a way modulates the frequency or changes the frequency. So this happens with the radar pulse that hits a layer of atmosphere and comes back. It gets shifted in frequency by the speed at which this layer of atmosphere is moving. And it's possible to do very careful signal processing and accurately measure this Doppler velocity, which tells you the wind velocity in a way. And that tells the atmospheric scientists some very vital information about which way the wind is blowing at a given altitude. And from that, they can figure out a lot of information about weather patterns, precipitation, rainfall, and so on. So what are the challenges here? The challenges are the transmitted frequencies could be quite high. That depends on how high you want to go into the atmosphere, which layers of atmosphere are of interest to you. So it can be as high as a couple of gigahertz. And there are applications we have done where it is as low as maybe 40 megahertz. So the transmitted pulse generation itself is a job that this box has to do. And some of you would know that to do this accurately, precisely, and in a stable way so that the frequency doesn't drift is quite an electronic challenge. And that's all done inside this box using the right kind of processing. Now, when the pulse comes back, we have to do its digital down conversion. DDC stands for digital down conversion. This is a combination of a low-pass filter, a decimator followed by a low-pass filter, right? So what you do is you reduce the sampling frequency of the signal and remove the out-of-band components that are formed by this, and that's how you do the digital down conversion. And then we do coding, decoding. There are several radars working at the same time, and signal to noise ratio and interference can be a problem. So a radar uses a specific code, and the receiver knows that that code, so it decodes that code. And this gives you a signal to noise ratio improvement so that you can go higher. By the way, radar signal processing is an extreme challenge of noise reduction because your target here is an atmospheric layer. So it's not a very hard target. The echo is not very strong. So inherently it is weak. And as you go high, the transmitted signal will fall 1 over r square, and the received signal will fall again 1 over r square. So higher you want to go, lower is going to be your signal in a very significant manner. And so all these techniques of coding, decoding, noise reduction, integration, etc., play a very vital role. Then we use Fourier transform because we know our transmitted frequency. It's possible to know the frequency band of our interest and do a Fourier transform over that band and get this Doppler spectrum that is shown on the screen. So this in a live situation is a spectrum continuously changing. On the right side of zero line, which is the center line of the spectrum, wind is blowing in one direction. On the left side, it is blowing in the other direction. So all this information then goes into some kind of weather interpretation or data generation model, and they generate interesting weather information. The frameworks used here are analog devices libraries because the F50s are all done on the Tiger Shark DSPs, so they have optimized library functions for this. And we have used Xilinx IP cores for implementing the digital down conversion, the gigabit Ethernet, and things like that. So that use of these things makes implementation of such systems relatively straightforward. I go to the next example. This is from the electro-optics domain, and this is a laser rangefinder. So what you see here in this box is the laser rangefinder. And It is using an avalanche photodiode as a sensor. Avalanche photodiode converts light into electricity, and this it can do for fairly weak optical signals also. But handling this APD can be a challenge. You need to carefully condition its analog signal output. You need to amplify it with a programmable gain. That's why the PGA, the programmable gain amplifier. And this output goes to a high speed A to D converter, and the A to D converter output goes to the Xilinx Spartan 6 FPGA. And this, like a radar, is emitting a laser pulse and getting back an echo. And it's finding out the time difference between these two to know what's the range of the object from which this signal has come back. And the main signal processing technique used here is pulse integration. So you can rarely get this kind of result with a single pulse. You keep sending the pulse again and again, and you keep on building your received signal through integration. So when you build a signal through integration, the signal builds, whereas the noise decreases. And this is a very basic principle of filtering. With that, we can get the signal reasonably above the noise threshold, and then we can detect it, and then we can know what's the time difference between transmitted and received signal, and know the distance. So this is an area around my office. So we transmitted from the roof of our building to another faraway building, which was by Google Earth, was about 1.021 or 1021 meters, and the instrument measured it as 1025 meters. Error could be on either side, but we believe that we are measuring with something like 1 meter accuracy in our system. And this kind of range finding is used in multiple applications, in surveying, in military, and things like that. So this is a good example of electro-optic signal processing. Here I show you a image processing application for industrial automation. What you see are pharmaceutical wires, and these are going on the conveyor belt, and they are being presented to a camera. This is a light source here, and the camera you will see soon. Yeah, you see here the camera, and what this system does is it looks for defects in these bottles. Here you see the image of a bottle, and any bottle that it found defective in terms of dimensions or any foreign body inside, like here there's a broken piece of glass, that kind of bottle is picked up by this rejector mechanism and thrown out of the conveyor system. So this is an automation application where bottles manufactured by a glass blowing process are automatically inspected and segregated into good and bad. So here, the sensor is a CCD camera, the actuator is a rejector mechanism, and all the processing is happening on the Pentium CPU. And the techniques used are this kind of image that the camera sees has to be segmented from its background. So we have to know the precise locations of this edge, the shoulder, the neck, the lips, and so on, and then perform digital measurements on this by software. So the principal technology used here is image segmentation, and the framework we used was the Intel Vision library. And of course, we have our own library for some of the very basic image processing jobs. So this is in fact one of our very early machine vision systems set up in India. And 4 such lines are used by this glass blowing factory for inspecting the vials they make. Now you can imagine a broken piece of glass inside a bottle as shown here. If it ends up getting filled with medicine and gets sold to a customer, how bad it is. So it's really very critical to inspect every bottle very critically. Then I come to a topic of short range radar. So this is a radar, the sort of radar that is used in automobile technology now. So this is you can see in this video, the 2 people are walking outside my office street, and they are spotted as 2 dots on the radar screen as they walk away from the radar. So this is the radar screen, and this is the video shot. Now here, I think this is a extremely interesting thing that's coming now. Almost every car in the future is likely to have a device like this, so that some kind of driver assistance or autonomous driving will be possible. So there are many companies developing these technologies. We are using the framework created by TI, Texas Instruments, and this is a MIMO core they have developed. MIMO is multiple input, multiple output. So there are 2 antennas for transmission and 4 antennas for reception. And there's a very tiny FMCW processor from TI, which implements what is called frequency modulation continuous wave measurement. So in this technique, the transmitted signals frequencies changed continuously, let's say linearly. And what you get back an echo also will be a linear change in frequency, except that it will be time shifted, because electromagnetic signal takes finite time to go to a target and come back. So we measure the frequency difference between the transmitted instant and the transmitted waveform and the received waveform. And that can be done relatively easily by a FFT algorithm. And that's what is done in this application, to know the exact location. So you see the car coming was clearly spotted by the radar. The 2 people are walking back. They can be seen as 2 dots. Now, the difference between camera and radar is camera won't work at night, whereas the radar will work day, night, foggy conditions, and so on. By the way, this radar works in millimeter wave frequency range. It's, I think, between 77 and 81 gigahertz frequency. And with as tiny as 12 dBm output, it's able to see almost up to 75 meters from the radar. So this is another interesting state of the art of the technology. I'll just show you 1 or 2 more. This is from our image processing team. Those of you who are in material industry or mechanical engineering tasks would know that every material has some surface hardness. And the surface hardness is measured by creating an impression on this surface with a tool. So in this case, the tool is a ball, and this ball is pressed on the surface of the metal with some known load. So in this case, I think it is a load of 300 kg. And that has made an impression on the surface of the metal. And it's the job of image processing system to measure the diameter of this round impression accurately. Obviously, the problems are shining surfaces like this. Then there is noise in the background. So this can really obfuscate the clear definition of the edge. And for this, you require algorithms which will really mark the boundary accurately. So our device is based on an ARM core, like a Raspberry Pi-like architecture board. And it uses a very low-cost USB CMOS camera. See, one of the hallmarks of such industrial applications is that they have to be low-cost. You can't be using very state-of-the-art hardware for this. And then there is a touchscreen display. And on that display, you see the measurements. And the techniques used are noise removal, this sort of noise you see here on the background, and image segmentation, that is segmenting this round from the background accurately. So our team has used the framework of OpenCV for implementing many of these algorithms here. And when we did manual to automatic measurement comparison, we found that we are well within the tolerance. I think they have a tolerance of more than 5%. So we are well within that. So this means that whatever human eye can do to measure the size of this impression under a microscope can be done equally well with a camera and an algorithm. So state of the art is almost that level that any kind of heuristics humans are running in their brain, they can also be implemented on these processing platforms. I think my last slide on video processing. The difference between video and image, or first to say the difference between image and signal. Image was a two-dimensional signal. It had X and Y, the spatial coordinates. Now in video, you have 3 dimensions. There's also time. So you have a sequence of frames that you're processing. And in this application, we have a auto-tracking pan-tilt zoom platform. So when it locks on a target, the camera moves with the target. As you can see, this friend of mine is walking around on the roof of our building, office building, and the camera keeps him always in the center of the screen. So there's no manual guidance here. It's doing this completely automatic. So technologically, it has got a CCD pan-tilt zoom camera. Its actuator is a pan-tilt zoom platform, which requires commands to either move to the right or to the left or up or down or zoom less and so on. And here we have used an analog devices Blackfin DSP. It's a 16-bit fixed point DSP that clocks at 500 megahertz for implementation of image processing algorithm. And we use the very famous Lucas Canade technique for image segmentation and some kind of Kalman filter so that the pan-tilt zoom platform moves smoothly and is not jumping back and forth. And you can see the result. This has got a lot of applications. Security cameras need this so that when they lock onto something interesting, they just move with the target. This can be used for advanced robotics, where the robot has to aim at something that's moving and do some industrial action. So it can be used there too. And as framework, we have used analog devices DSP library. So I assume that this is giving you a fairly good idea of the state of the art. I now would like to take a little bit into the future and if we check the time, I think we have 10 minutes more, so we should be able to. We have 10 minutes more, right?
Yeah, yes, sir. Yes.
Yeah. So this is a head tracking application, and the sensor technology I'll be giving you more details shortly is a time of flight camera. Now, what this camera does is it gives you not just the light intensity at a point, it also gives you distance to that point from the camera. And how it works, we'll see a few slides down this presentation. The interesting thing is, because it gives you distance, I think it's going to change the way we look at electronic technology, giving us information about our surroundings. All along, we've been getting only pictures. Your camera gives you just a picture. It doesn't tell you how many meters is the door from your camera. It doesn't tell you how many centimeters is the table from you, and so on. Whereas this time of flight camera has that ability, it gives you distance direct. So we have used this sensor, and the actuator is just a display because it's a head tracking application. It's a x86 PC that's used as a processor. And what we use is a concept called point cloud, where the point cloud is a cloud of points where you know the X, Y, and Z coordinates. Because the camera gives me the distance, it's possible to map the scene as a point cloud. And imagine segmentation of a point cloud is so much easier. I'm wearing a white shirt now. If my background was completely white, a normal camera would probably miss my shirt's outline because it will merge with the background. But suppose you were looking at me through this time of flight camera, and you knew that I'm sitting roughly at a distance, a laptop user sits from the laptop, then putting a threshold on distance of more than, let's say, a meter will completely remove the background from me. So even if my shirt color matches with the background, I would still be able to segment myself very accurately from the background. So this really is the USP of this technology. So one of our engineers put together a quick head tracking demo with this. So you can see he's moving his head at pretty high speed. This frame rate is almost 18 frames per second, and it still doesn't lose the track. The box remains around the head. And that's because from the camera, we are not using the color or the intensity. We are using the distance. And the distance profile of a human head has certain characteristics. Obviously, human head cannot be like a rectangular box, nor can it be like an exact cone or a pyramid. It has certain shape. And this shape can be defined as a template in distance, and we can accurately locate this. So while moving from very simple audio application we started a few slides back, we have come to a point where we have a video processing application where a very recent time of flight kind of imaging camera is used. More about this technology, as I said, we'll see later. So I hope this gives you a good idea of where the technology rests today. So just to summarize, a few points that I didn't mention, I'll mention here. The processor technology, I think that is really changing at a very, very rapid pace. Today, my team is working on a system-on-chip concept where microcontrollers, FPGA fabric, and dedicated DSP blocks all exist on the same chip platform. So it becomes extremely easy to transact high-speed information between them and implement your fairly complex number crunching application on a tiny device. So we are using many of these processors. Just a few years ago, many of these applications used to be bare metal, in the sense that there's no operating system or kernel to support the programmer. Today, I think that is changing in a very dramatic way, that you get extremely good kernel and operating system support on such high performance devices. And it then becomes easy to use libraries to import components that some other people have developed or are using in some other systems and use them in your system. So this is really changing in a big way. I didn't give you any example of deep learning. I have not deliberately put them on the slide because we are still not as matured as we think we should be. But our team has already done things like one industrial application where we are doing X-ray imaging of some objects. These are food objects. And we find automatically if that food object is good or is spoiled. And it uses a deep learning technology on X-ray images. And it segregates this good and bad food items very rapidly. So these are the things that are really changing very rapidly. And on sensors, as I said, from very simple implementations to very complex implementations, we have moved in the last 50, 60 years. One of them about time-of-flight imaging we'll see shortly. So I hope so far it's going good. Can I get some feedback from the other members?
Yeah, sir. The questions are coming. One Mr. Arvind Rathod is asking, can we use cameras for identification and tracking of corona patients?
See, again, I'm not really an expert in that field, but what I have seen outside is the symptoms. One of the major symptoms is body temperature. And you all know that these thermographic devices are used for segregation of potential symptomatic people. So at airports, you've seen thermal cameras, and they can locate a warmer skin quite quickly. It doesn't mean necessarily that the person is infected by coronavirus, but certainly means that the skin temperature is higher than normal, and then other tests can confirm that. So to Mr. Rathod, I only can say that I am not aware of any sensor that externally can detect the presence of coronavirus or infection of coronavirus. And I think world over they are coming up with test technologies, which I believe are based on some samples. So saliva samples or something like that. And these are processed to find if there is virus in it.
Yeah, Miss Priya, she's asking, how can we apply filters in images for live pictures?
Live pictures.
Yeah.
Okay. Yeah. So this is an interesting question. So a live picture is also, in a sense, sampled in time. So as I was saying earlier, difference between image and video is image is a two-dimensional frame, whereas video is a three-dimensional picture signal. So to convert that into three-dimensional picture signal, we are cascading images one after the other. So video is nothing but a set of frames, right? Now, the popular encoding techniques of video do not actually manage the video this way because they do frame-to-frame compression and things like that. The file that is saved may not have explicit bunch of images, but there are a lot of software libraries available to convert a video into bunch of frames. So a 1 second long video shot at 25 frames per second can be converted into 25 images by using such software. So in which case your live video is a folder containing 25 image frames. And if your filter is a static filter, that means its coefficients are constant. Let's take the simplest, most well-known image processing filter, that is Sobel filter, which is doing the edge detection. So its coefficients are constant and its threshold is probably set once, is remaining constant. So you can apply this on every frame and you get edge detected every frame. And then there is a reverse piece of software available which can convert these 25 edge detected frames into a video. And this video then becomes a filtered video, so to say. So conceptually, it's pretty simple that we apply the filter on every frame from the video.
Okay. Another question from Ms. Maheshwari. Can DSP processor meet the demand of high performance computing the way GPU do?
Again, I think a very interesting discussion. There will always be like it's a little bit like every architecture has its own pluses and minuses. So DSP definitely is used for high performance computing. I think many examples I showed in my earlier presentation would confirm that these are all high performance computing in the sense that whatever is the clock frequency of the DSP, we are using every cycle at that clock frequency for doing one or the other operation. So there's no idle time there, right? Yeah. Now, GPU, on the other hand, is architecturally a very different thing. It's implementing parallelism at a very minute level. So the way you think to use a GPU is completely different than what you would do with a DSP. So again, I'll give you an example. Let's go back to that Sobel edge detection. You do something like 2 3x3 filters or masking operations in a Sobel edge detector. Now, if you're using DSPs and you want to speed this up, you would use multiple DSPs and give parts of images to every DSP. So let's say you use 4 DSPs and 1/4 of the image was given to every DSP. Your application runs 4 times faster. That's no brainer. But in a GPU, what you would do is look at the 3x3 mask and how that 3x3 mask, whatever multiplications and accumulations you're doing, how they can be parallelized on a processor, on a very simple processor. It can only do multiply and accumulate. So you would use larger number of such processors, but you would get parallelism at that very minute level. And there are, of course, pluses and minuses. The former technique of DSP would work only if you have very large amount of data and you want to do a small amount of processing. Whereas on a GPU, a relatively small amount of data, but very large amount of processing also it would work. So I think in answer to your question, yes, of course, DSP can be used for high performance computing, but I won't pitch it against GPU. I think both can be useful.
Okay, and the next question is from Mr. Arun Kumar Mishra. How can we do faster analysis by any means other than this RT-PCR method?
This is for the, can you just explain the question once again, because I didn't understand. RT-PCI, what is that?
RT-PCR method. Then this RT-PCR method, the method that you have shown in your presentations. How can we do faster analysis by any means other than this method? Okay.
Which application is it talking about? Because I still don't understand.
Okay. I will take more details from you. The next question: how to measure distance between camera and object in live shoot?
Correct. That's the topic of next few slides. So if you wait for just a few minutes, you will get it.
Okay. The next question is: can we identify viruses through high resolution camera? Again, similar question, right? The previous first one.
Not to my knowledge, unless this is a lab situation. Lab situation, obviously you can, because whatever kind of deadly looking images we have seen of coronavirus, obviously has somebody captured them through a microscope or a suitable device and with a camera, with a high resolution camera. But not in the live condition as one would imagine that. Probably the aim of this question is, can I put a camera somewhere and it says that, hey, there is virus on that table? No, that I don't think that's possible.
Okay. The next question is, how can we detect ages in videos?
Ages?
Yeah.
Age of a person.
Ages?
Age.
EDG.
Okay.
EDG, yes. Ages.
Yeah. As I said earlier, the edge algorithm can be run on every frame of the video. And you would get edge detection done on every frame. In fact, you can look at our website, and we have some YouTube videos where we do live edge detection on a video by this technique. That edge detection is performed on every frame of the video, and it is put back as a video. But just in a sort of addition to that answer, I would say that you can also do some kind of frame-to-frame connection. So, for example, if there is a very strong edge in one frame, it's likely that in the next frame it won't vanish. It might move a little bit, it might tilt, or it might become weaker or whatever, but it won't completely vanish. So it is possible to do edge detection on every frame and apply a heuristic on the detected edges so that the breaks are avoided. So there are no drastic changes from frame to frame. And I think this is what they do in many special effects you see on television, and you get very smooth edges moving as the person is talking or is running or is moving. They do some kind of extrapolation between frames to sort of make it look smooth.
Okay. The next question is, sir, is there any benchmark data set which is available for mammogram image?
Personally, I won't know directly any link, but I've reviewed a couple of works earlier, and they have always referred to such sets available. And there are also a lot of medical facilities in India who are very eager to connect with image processing fraternity and do something new. So if you actually approach a clinic, I'm sure they'll give you a lot of data. That's what I've seen many of the researchers I have met do, that they approach the local medical facility and get the images.
Okay. Then next is there any interface required for MEMS sensors?
Yeah, so the one I think we used in this Mobidio application has a digital output. So you probably know an interface called I2C. This is a inter-IC kind of communication on a board. So it is just 2-wire. You have a clock and a data pin. So it's that kind of interface that this microphone gives, the MEMS microphone. And I believe most MEMS devices provide data interface, digital data interface this way.
Okay. The next is, how huge amount of data can be handled while processing videos?
While processing?
Videos.
Videos, oh. Yeah. I don't think there's any limit there. See, it's this way that the architecture of what you do plays a very important role. So I'll give you an example. If I'm doing a live video processing application, I would have a separate process, maybe a thread that's interfacing with my incoming video source. Then I would have a separate thread for implementing my processor and a separate thread to create a video out. So by these three separations, it is possible to run the three processes completely independently. And it's not as though that we are going to use a processor which will not be able to process even one frame of the video. So I'm assuming that we are using a reasonably good processor. Then implementing this kind of separated processes model makes it really independent of what is the size of the video, because as one frame is coming in, another previous frame is already processed, and one before that is already sent out to the output process. So if these threads are synchronized well with reasonably sized buffers, so that in case something goes out of sync, there is no overflow, then I think video size or its duration doesn't matter.
Okay.
Your tiny cell phone, your tiny smart cell phone is playing videos of any length, right?
Yeah. Okay. It's again we'll take a last question. Remaining questions we'll provide. We'll send an email to you and take the answers. But the last question from the faculty point of view: what is the level of proficiency expected in graduate students so that he is able to do well in signal processing industry? How we can give the input so that he will be proficient in the signal processing industry?
This is, I think, a question that can be answered as a full talk, probably, or not one talk, many talks. A very interesting question. I think the first and foremost is just the interest. I don't think there is anything more than that, you know. And the reason for that interest can be very many. Somebody wants to do something nice, scientific. Somebody wants to become career-wise advanced. Somebody wants to earn a lot of money. The objectives may be very different, but I think that very strong interest is what is required. Especially in signal processing and image processing, the techniques part of it is slightly mathematical, because inherently what you are doing in any of these signal processing jobs is that you are deciding fate of some point based on surrounding points before and after, right? And this means there is always going to be some kind of arithmetic connection between past, future, and present. And this is mathematics. So if the interest that person has is also a little bit in mathematics, is not worried about mathematics, is eager to code all that simple mathematics into programs, then I think success is guaranteed. In my view, I mean, why I got into this is most interdisciplinary. I think the 5 examples I showed you, they are all from different fields. And what more a person wants in life is, you know, to know more and more about different disciplines. So this gives you the best opportunity to do biomedical, to aerospace, to defense, to industrial automation. Come what may, I mean, you will have an opportunity. So I think it's a very interesting field. Your own hunger for doing something based on or in these domains required. Very hard to judge though, and so I don't think there's a simple answer to this, that if you can solve this problem and you are a good engineer. There's no simple answer.
Okay, I think there are a lot of questions. We'll collect all those questions and email to you, and probably we'll
also have a opportunity tomorrow, because that will be more on applications. So let me get on with this quality attributes and just what I want to talk about the new imaging technique.
Yeah.
So since you asked this question about what makes a good signal processing, image processing engineer, is I think besides all that techniques and filters and all that, you know, one would learn in college, once you are in industry, I think probably the benchmarks are different. And I think we have about 20-25 such attributes which we keep in our company, and every project is guided by some attribute. So I have just taken liberty to write 5 of them here. And I think quality attribute of a signal, image, or video processing system would be response, the topmost. It's a measure of quickness. So how fast can your system work? So 100 megahertz, can it work at 200 megahertz? Can I drive my clock at 300 megahertz? What would be the change required? Will I get a better performance? And how can I ensure that the better performance is achieved? So all these things are always the topics of importance. These are real-time systems, by the way. When you're talking on your cell phone, you don't want to hear your friend's voice after a minute. You want to hear it instantaneously, right? So that being the constraint, that whatever it takes to work on the sample that's going to the loudspeaker which you hear has to be done within that sample time, which may be just a few microseconds, you know. So response takes a very primitive or premium position in this work. And this is where I think optimization plays an extremely important role. So again, you asked what an engineer should know. A little bit of optimization of code, you know. So I mean, ask someone to write a code who knows, let's say, how to write a for loop and things like that. We'll obviously do that. But maybe some experience in the industry tells him that this is probably not the best or the fastest way. There could be things that can be optimized. We can use the library function. There are string copy or memory copy features available in most operating systems. If I use that, then maybe my arrays can be copied much faster and things like that. So I think a focus on all such things is required. One of the guidelines we always give to our engineers is look at every calculation you do in your code. And if that calculation is a fixed calculation, let's say I'm multiplying something by 3. Yeah, my code is B is equal to 3 times A. Is it necessary to actually do it this way? Like a real multiplication in every loop of the for loop? I might as well ask how many values A can have. And if A can have only, let us say, 100 possible values, I might multiply all those 100 by 3 and create 100 multiplied results, keep them ready. And then I'll use A as an index and just pick 3A from the table. So this is called a lookup table. And I gave a very simple example of multiplication, but there could be other opportunities where this can be done, that the inputs are only finite. I'm doing something very complicated with those inputs. I should ask a question, should I do it in real time or should I do it in advance and store it as a table and just pick it up from the table? So these kind of techniques can be used to improve the response of a system. Responsiveness. This is I think from practical use point of view, probably the most important quality attribute, that how you handle success and error conditions. You'll be extremely annoyed if your cell phone once in a while, every half an hour says that, sorry, exception, rebooting or restarting, right? So be assured that it's happening inside, but it's not reporting to you in a graceful way, right? So there is a extremely high amount of responsiveness built into the algorithm so that a failure is handled in a way that you don't notice it. It gets bypassed. And only in a very extreme condition, it gets nicely alerted so that you know what button to press so that you come out of this condition. So for an engineer, I think it's very important to know this. Code-wise, this means that every condition in the code is handled. So again, a student, you ask him to do some job and say that is a math library function, you have to call that. He'll simply call that function without realizing that return value of that function is giving a lot of information, that whether it went through correctly or it had some problem or it had overflown something, this and that. So very important to check the return values and then write code so that those return values are suitably handled. And this I think in most entry-level codes, this is a problem that we see, but this needs to be done. Accuracy, degree of closeness of measurements of a quantity to that quantity's true value. This is very critical in image processing because a small change in R, G, or B values can change the color of that pixel as is apparent on the screen. Or in industrial applications where I'm reading a process parameter and its value changes, because of accuracy issues. So one typical example is A to D converter. Most of us think that 16-bit A to D converter means 16-bit accuracy. Actually, it is not. There's something called effective number of bits that the ADC gives. And for a 16-bit ADC, it will be really good if you can get more than 13 effective bits. So how to calculate the ENOB, how to interpret that? These become like topics that need to go into your design considerations. All these quality attributes are design considerations. So you design your software or design your system so that these attributes are met. In our projects, we tell the engineer that this is the project, and in this, out of 20, these 3 are the most important quality attributes. At the end of the implementation, you have to tell us that how these attributes are met in the design. And if that is really convincing, then only it is worth really taking this further. Then come the quality attributes of reliability. Again, don't want failures. So mean time between failures has to be very, very long. In a system, let's say like a cell phone, it depends on many factors. So there's a battery, there's some hardware, there's a display, there's a keypad, and all kinds of things. So there is a whole bunch of scientific principles for calculating mean time between failures for a combined system of this kind. And I think knowledge of this, or at least a top level goal setting for this is important. And finally, most important, maintainability. Our systems are deployed world over. It becomes extremely difficult to change its firmware or give an update or reprogram some parameters, recalibrate it. We can't be traveling all the time to do this. So the system design has to be such that it can be done remotely, right? So I'll leave this here. There are those who are interested, we can talk offline. We have, as I said, more than about 20 such attributes which we consider before design. Then I come to the last, I think, topic before we talk about time-of-flight imaging, and that's the importance of simulation. We often think that why I think humans are able or have evolved in a certain way and able to do such amazing things as compared to other species on Earth. And I sometimes think that it's because our ability to simulate. I think when we are not doing anything, constantly we are simulating in our head that if I had done this, what would have happened then, and so on. So it's actually what's happening internally, some kind of internal MATLAB is creating a model and creating a simulation, creating a simulated video, and that's running through your head, knowing that if I had said so and so, the other fellow would have got angry and something like that, you know. So, and I think our ability to judge is improving because of such simulation. And the same thing can be brought to the engineering field, especially in signal image video processing, where simulation is a very important. So for us, I think, again, 5 factors. It gives us a lot of test data. So synthetic simulated test data. As I told you, first wind profiler radar we built, we had no data. So we actually built a model of atmospheric layers. We actually built the model for wave propagation to a certain height and reflection. So we could generate whatever sine wave we wanted in our MATLAB simulation, echo it from the layer, get it back, see the frequency shift, and so on. And that's how we actually generated megabytes of test data when there was no radar. It was all in our head only. So I think it's very important to have this synthetic test data. More often, I think people come and ask us about their projects and thesis. We tell them that start with synthetic test data, so that you know what the result is supposed to be, get that result first, and then apply it to the real data. I think this is extremely crucial now because deep learning frameworks require a humongous amount of data. And it's not always possible to get real data. So it may be possible to simulate such data and train a network with that. Algorithm scheme can be simulated. So I mentioned GNU radio, for example, allows you to do a complete software-defined radio at schematic level, and then convert it into working code. Algorithm characterization, how well it works, how accurate, how precise, what's his dynamic response, how it depends on external factors like temperature change or rainfall and things like that. We can simulate and characterize our algorithm. Failure analysis becomes extremely easy to test once you have simulation. So if I have a complete simulation, I can give a deliberate overrange input and see if the system is crashing, right? Or will it do something unexpected? So this kind of failure analysis is possible. And finally, system generation and verification and validation. These are the steps that are much easier to do on a simulation rather than on a real system. And once you've done it on simulation, carrying them out on a real system with simulation as a reference becomes once again very easy. So these 2 slides I shared just to sort of give our perspective on implementation approaches. Now, I think we have exceeded our time. I'm sorry for that. So I'll take just 5 minutes to tell you about the new technology.
Yes, sir, sure.
So here it is. The time of flight imaging sensors. So the left side here, it talks about 2D cameras and 3D cameras. 2D camera for a scene like this, where there is a cylinder, a half sphere and a cone, camera is looking from the top, would produce a flat image like this, right? It's a projection. The depth information is lost. Whereas a 3D camera would produce an image like this, where the color is giving you the depth or the Z axis. You see my cursor, right? Moving on the screen. Do you see my cursor moving on the screen?
Yes, yes.
Okay, yeah. So 3D image, obviously, apart from the spatial variation, is also going to give you the depth. And now there was a question, how do you get the distance from the camera? So let's answer that. So this time of flight imaging has multiple ways to do this. One of the best known methods is stereo imaging. Like humans, we see 3D because we have 2 eyes. If we had only 1 eye, we wouldn't see 3D. And our brain is from childhood trained to create a match between the left and right eye images. And it finds how much is the mismatch at a given point. And from that mismatch, we learn to judge distance. So a very far away object would have less mismatch, and very nearby object would have much larger mismatch, owing to the separation between 2 eyes. But this technology obviously can be implemented with 2 cameras, but has a problem that it is very significantly impacted by things like light changes and shadows and things like that. So although it is used, it's not the best. There are other technologies like structured light. Many of this gaming stations use structured light cameras for that, where a pattern is laid on the object. So there is a light source, and it's, let's say, putting dots on your body. Obviously, these dots will shift depending on the 3D profile of the body. So a profile region which is closer to the camera, the dot would shift one way, and which is away, maybe it will shift the other way. And from these dot shifts, it is possible to figure out the depth. But again, it is very dependent and on your ability to match the dots and so on. So this is again not a very good way of getting distance. So what you see in our time of flight sensor is an indirect phase measurement to know the distance. So the camera is a camera. It's like a CMOS or a CCD array, where these little squares here are nothing but photoelectric photocells. Light falling on that is converted into electricity. But it's not ordinary light that's falling on it. What we are doing is we have a RF generator which generates what is called a modulated light. And through this lens, it falls on the scene. Now the scene is 3D. The distance is changing from camera. Now this modulated waveform reflects, and through this lens comes and falls on the matrix. And the modulating waveform here is used to demodulate on each pixel. Now with some signal processing background, you can understand that this will measure the phase shift of the modulation as it has traveled from here to here and come back here. So if this distance was d, it has undergone a phase shift equal to 2d. And this can be measured by signal processing, as you will see in the next slides. So the technology uses this modulated waveform, and it uses actually multiple channels, that is A and B, 2 channels, so that the net output signal is the difference between the two. This takes care of what is called the ambient light. So if there is some ambient light in the room, that since it is not modulated, it's just going to give a shift in both these signals. Both signals will shift up or down depending on ambient light. And if I'm taking always the difference, then the ambient light gets cancelled. Similarly, for reasons of inconsistent silicon doping and things like that, we do not use a simple modulating waveform. We use modulating waveforms at different phase shifts. And with this, the calculation is implemented inside the camera, either on a microcontroller or an FPGA, to calculate the distance as tan inverse of the phase shift, and the distance can be calculated from the phase by a simple formula. We also can know what's the reflected light intensity by this amplitude calculation. Those of you who are in signal processing already recognize this as polar. This is the Cartesian to polar conversion, and this can be implemented by what are known as popular Cordic algorithms in real time. So this was one of the early cameras we developed. What you see here is the light source. These LEDs are switching on and off the light at a very high speed. High speed meaning it can be 40 megahertz, for example. So imagine the light is turning on and turning off at 40 megahertz, 25 nanoseconds, right? Now this light travels, hits some object and goes back through the lens into the sensor. This is the sensor inside. There is a FPGA on the board, which does all that Cordic algorithm and all that. And so that for a camera like this is the output, where the color gives me the distance of the object from the camera. So deep red is close, and then blue will be very far. So you see a quick video of this. This is in one of our labs. So you asked how to do this in live. This is happening in live. So as the hand comes near, you see that it's becoming deep red. It goes away, it becomes light red, orange, green, yellow, and far away is black, where it doesn't see, the reflected light doesn't come back at all from there. You see that deep red hand when it comes near the camera? So the camera, apart from this reflected light output, is also giving me a distance output. And this is a huge thing. With this, a lot of interesting applications can be done. So tomorrow when we meet, I'm going to show you robotics and such applications of this technology. Today, let's see something that's done by a few partners. So you see here this camera. This is the right camera, and the hand is moving in front of the camera. You see its depiction on the screen. It's able to understand occlusion and things like that, exact orientation of the hand. Then the same camera is detecting gestures. So you're not touching anything, neither the keyboard nor the screen, but the cursor is moved by just the fingers. So next frame. So in today's world where touch has become a big problem, I think a technology like this is going to be very useful. So there's a very interesting version of this technology for cell phone application. Those of you who are interested, you can look for Google Tango, Tango, Tango. And a couple of cell phone companies already have got this in a cell phone. So it's possible to do a virtual reality model of your home by just taking cell phone shots, and it will know the exact size of your room, what's the floor area, what's the height, and things like that. Because the images here are also getting distance to different points in the image. So this is the future of imaging. Today, it is at a resolution of about quarter VGA, so 320 by 240 pixels. And I'm very sure it will grow in the years to come. And just as humans see distance very naturally from the eyes, the electronic cameras will also start seeing that. And we can really change the way we do image processing. So thank you. So really appreciate your interest. If there are some one or two questions, if there is time, of course, I'll take them now. Otherwise, we can continue this tomorrow.
Yeah, we'll take the questions tomorrow, sir.
Okay. Yeah.
There are a lot of questions. That's why I will take all the questions tomorrow.
All right.
I have just listed all those questions. And
yeah.
I will send it to email to you, and then we can discuss it tomorrow.
Sure.
Okay.
So thank you, sir. Thank you.
So I interest and in line with your expectation for the program you have made. So I really appreciate that and like to wish you all the best for the other talks in this program, and look forward to talking with you again tomorrow. Yeah.
Yes, sir.
Thank you.
Amrut.
Good afternoon all. Good afternoon all. Myself, Amrita Moite. My greetings to all of you. I'm honored and lucky to have the opportunity to give a vote of thanks of today's first session of Signal Image Video Processing, a Practical Approach 2020. Today my words are not enough to express the gratitude. On behalf of EMDC Department of Government College of Engineering, Karad, I would like to thank our today's speaker, Dr. Udpikar sir, who graced us with his thoughts, provoking the address to set a perfect platform for our college as well as our department. Thank you very much, sir, for your guidance. We have been fortunate to be assisted by our beloved principal, Dr. A.T.P. sir, who have been a constant support and given us a lot of encouragement. Thank you very much, sir.
Tomorrow we'll start our session at 10:30 in the morning.
Thank you very much, and wish you all the best.
Thank you, sir. Thank you.
Thank you, sir. Thank you. Thank you. Thank you, sir.
Moving towards the second session, it's my privilege and pleasure on behalf of ENTC Department of Government College of Engineering, Karad. I welcome you, all of you today. We are delighted to have Dr. Sriram with us to share her knowledge in our Signal Image and Video Processing, a Practical Approach 2020. Now a short introduction of ma'am. Dr. Sriram is working with Cummins College of Engineering